All right, let's just do an example here. So let's look at computing the double integral over the region R of the function 5x squared plus y dA. Okay, we gotta write that at least. But what's R? So we need to describe what R is. Where R is, and then I'll draw a picture to show you what R is. So I've got here some x and y axes. I've got 2 and 4 labeled here, and here's what I'm going to do. I'll draw dotted. Ooh, let's just try to make that look really much more circular than that. Apologies. Like that, and like that. And here's what we're going to do. Actually, continue this around like this. Okay, and then continue this around this way. So maybe I'll use a new color. This region filled in there, that is R. Okay, so that is capital R. Okay, so in starting the answer then, first, not that we have to write it this way, but let's write what R looks like. Described in polar coordinates anyway, this should be the set of all points of the form r theta in polar coordinates, where r is stuck between 2 and 4, and theta is stuck between pi over 2 and 3 pi over 2. Okay, so just matching things up to the notation from earlier, I think the book has been traditionally calling that A and this B. Pi over 2 is the alpha, and 3 pi over 2 is the beta. So what we'll do in setting up this integral, double integral over the region R of 5x squared plus y dA, what is this going to become for us? It's going to be, by the way, the integral is going to end, so we're going to have the d theta integral on the outside, just as a spoiler alert. So then these theta values, pi over 2 and 3 pi over 2, should end up here. We'll talk about a little bit later why the theta is the outer integral. Let's just go with it for now, and then there's also a way to swap, but let's not go there. The inner integral will be the r integral, and it will go from 2 to 4. Okay, and then instead of just writing 5x squared plus y here directly, we're going to replace the x with r cosine theta. So r cosine theta, quantity squared, plus, and then y is going to get replaced with r sine theta. Okay, so then that whole thing, then the dA, this is the part that gets replaced with r dr d theta. Now, I think depending on who you may have taken a calculus class from in the past, the parentheses that are written here and thus here might have been done a little lazily. I think right now, let's say that these parentheses, parens, are necessary. Well, why? Because we're going to now talk about taking this r. I know it's strange because the r seemed to grow out of the dA, but this r is just a plain old, it's a good old r, just like this r is here. And we're now just going to distribute this r. Okay? And so if we do that, we're going to get, oh, by the way, these are the theta values because of the theta over here, only because there's a typical traditional order of that dA is r dr d theta in that order typically. So with the d theta at the end, it's the integral at the beginning. Okay, let's distribute that r though, right? So we'll have integral pi over 2 to 3 pi over 2, integral 2 to 4. Distributing this r, we're going to have 5 r cubed cosine squared theta plus r squared sine theta dr d theta. Now, we should integrate the inner integral, and I get that this is polar coordinates and all, but pretend it's not. Pretend we didn't even know this is polar coordinates. I mean, r is just a variable. So what you should do is integrate with respect to r, which is actually not going to be so bad, right? Because r, so if r is the variable, then and theta is a constant, then cosine squared theta is a constant, and sine of theta is a constant. So to integrate this with respect to r, keep this outer integral, right? Pi over 2 3 pi over 2. So integrating with respect to r, we'll have 5r to the fourth over 4 cosine squared theta plus r cubed over 3 sine of theta, and we evaluate this at r equals 4 and r is equal to 2, and there's still this d theta at the end. Okay, we'll just scroll a little bit. And now, just to write this with a bit more space, we've got to plug in r as 4, right? And then plug in r as 2. So, what? Like an integral pi over 2 to 3 pi over 2. Plugging in 4 first, so 5 times 4 to the fourth over 4 cosine squared theta plus 4 cubed over 3 sine of theta. Then plugging in 2 for r everywhere, 5 times 2 to the fourth over 4 cosine squared theta plus 2 cubed over 3 sine of theta. Technically, that whole thing is in parentheses, d theta. Okay, at this point, there are a lot more technical steps to do, but I'm just going to leave it at the following. So integral pi over 2 to 3 pi over 2 of, let's just do the following here. How about 5 times 4 to the third, and then cosine squared theta can actually, using a trig identity, be rewritten as 1 plus cosine of 2 theta over 2. And then there's still this plus, 4 to the third over 3 sine theta. Sure. And then minus, let's see here, what do we have? 2 to the fourth is 16. Yeah, over 4, so 8. So 5 times 8, so 40. There's another cosine squared theta. Okay, so we'll write that again as a 1 plus cosine of 2 theta all over 2 plus 8 thirds sine theta, close parentheses, d theta. There's certainly more work to do here, but I think this is a good place to stop. The point being that this integral, while still messy, you break this up into 4 separate integrals to do. Where you see the 2 thetas, you got to do a u substitution and so on. So there's more work to do, but I think at this point we can see our way out. Here's the point at which I'd like to ask the interactive question. I know you've only seen one polar integration problem here, but I'd like to still ask anyway. I want you to just build a hunch. So what kind of shapes would probably be set up in polar integration as opposed to using rectangular integration like we've been doing so far in this chapter?